Drive microbes to evolve drug resistance, then we can also make them evolve in ways that benefit us. This is the radical proposition of Amherst biologist Paul Ewald.
When people are looking at the antibiotic resistance problem, they see evolution as sort of the bad guy. It's the evolutionary process that's led to antibiotic resistance, and that's true. But just as easily, we can have evolution being the solution. In other words, we can have evolutionary processes leading to organisms becoming more mild.
Disease organisms evolve to be more or less harmful depending on how they are spread. Microbes that depend on close contact between people tend to be mild.
The rhinovirus that causes a common cold is transmitted by people walking around sneezing or coughing on other people. Since it really does depend on fairly healthy people to be transmitted, not surprisingly, it's one of the mildest viruses that we know about.
But microbes that are transmitted by insects or by tainted food or water tend to make people very sick.
The worst of all of the diarrheal bacteria that we know of have been waterborne. The bacteria that cause cholera and typhoid fever are often waterborne. So even if the organism is so harmful that the sick person can't move from bed, the organism can still be transmitted to large numbers of people. Once we understand the factors that favor increased harmfulness and decreased harmfulness, then we can look at all of the things we do in society. And we can ask the question, are we doing certain things, or can we do certain things that would favor organisms evolving towards mildness? We can look at the cholera outbreak in South America as a kind of natural experiment that allows us to evaluate these ideas.
In 1991, cholera invaded Peru and spread quickly. Over the next 5 years, more than 1 million people were stricken with diarrhea and vomiting, some severely. Over 10,000 people died. The disease was transmitted through water contaminated with human waste, or through food that was washed or handled by infected people. Ewald collected strains of cholera bacteria from South America and measured the amount of toxin they produced, an indication of their virulence. Over time, he would document evolution in action.
If you have contaminated water allowing transmission, we expect the cholera organism to evolve to a particularly high level of harmfulness, and that's exactly what we see. We find that bacteria that had invaded countries with poor water supplies evolved increased harmfulness over time. They've actually become more toxigenic. They produce more toxin than they did at the outset. If instead we clean up the water supplies, then we force the bacteria to be transmitted only by routes that require healthy people. And what we find is that when cholera invaded countries with clean water supplies, the organism dropped in its harmfulness. Those bacteria evolved lower levels of toxin production. They actually became more mild through time. People would still be getting infected, but the infections would be so mild that most people won't even be sick. So the cholera outbreak in Latin America suggests that we may need only a few years to change the cholera organism from one that would often kill people to one that hardly ever causes the disease. What we're suggesting here is that we can domesticate these disease organisms very much in the same way that we've domesticated other organisms that are potentially harmful. For example, wolves have been harmful to us throughout our evolutionary history, but through domestication, some wolves have evolved into dogs that instead of harming us, actually help us. And I think we can do the same thing with these disease organisms.
Working with evolution instead of against it, we might eventually subdue even the deadliest microbes. Evolution has already forged such surprising truces.
Okay.
Most wild cats have evolved a way to live with a virus closely related to one that is decimating humans. The story was unraveled by Stephen O'Brien, here at the National Zoo to examine a tranquilized cheetah.
Well, we originally became interested in the cats because I was interested in the interplay between infectious diseases and the genes of the species that suffer them. We began working with cheetahs and subsequently started to study each of the 37 different species in the cat family. What we're learning from them is that they are mirrors of evolutionary processes in humans.
It all began in the 1980s, when O'Brien became concerned that small populations of endangered cats were especially vulnerable to the ravages of infectious disease. Then he heard that domestic cats were falling prey to a newly discovered and lethal virus, the feline immunodeficiency virus, or FIV.
FIV is associated with very skinny and malnourished and wasting disease in house cats. And that disease was the result of the collapse of the immune system. So the parallels with human immunodeficiency virus were very strong. I was curious as to whether or not the virus had also been able to infect non-domestic cats.
O'Brien had collected biological specimens from thousands of wildcats around the world. He began to screen them for the presence of the virus.
Well, when we did that in cheetahs from East Africa and the pumas in the Rockies and the ocelots down in the Andes and the lions in the Serengeti, it turned out that virtually every species of cats on the planet had been exposed to and infected with a version of feline immunodeficiency virus. Well, I was terrified because I thought that we were just a heartbeat away from an epidemic that was going to decimate some of these cats. And since 36 of 37 of these cat species are already considered endangered or threatened, then this could be the final wallop.
For years, O'Brien feared the worst. He urged zookeepers and game wardens around the world to test their animals for the virus and to watch for AIDS-like symptoms.
What we discovered, though, over time, is that these cats were really not getting ill. It was as if they had somehow come up with a resistance to a fatal virus.
O'Brien's research suggests FIV first infected the cat's ancestors around 1 million years ago. It decimated the animals. But a few cats carried mutations that made them resistant to the virus. These survivors passed on their protective genes to